Today's lesson is going to be on uncertainty, quantifying error in our measurements. Hopefully you had a chance to check out the previous videos on significant figures and accuracy precision because you will need that for this lesson. Otherwise, you would have covered this in class. Remember, in the previous lesson, we estimated the length of this line, and most of us got between 10 centimeters and 20 centimeters. However, in order to account for all the values that we estimated in between, it is more appropriate to write our value in terms of a range. So when we want to write it as a range, we include this little sign, the plus minus sign, suggesting that we are uncertain about the actual value. In other words, we're writing our value with an uncertainty. It shows that we are not confident with this value, but we are confident that's within, our value is within 10 centimeters and 20 centimeters. The smaller our uncertainty, the more confident we are with our measurement. The more confidence we have, it means that our measuring instrument is more precise. So less error, more precision. Let's take a look at a few examples, how we can use uncertainty in our measurements. How do we determine uncertainty in our measurements? In this particular case, we're going to look at single readings. So not yet repeated trials. For stable readings, you measuring the length of your pendulum is an example. With our measuring device, we want to estimate the last digit that is 1 decimal, using a different color pen, 1 decimal smaller than the smallest increment of your measuring device. Don't worry, we'll look at an example soon. Number 2, write the uncertainty as plus minus half of the smallest increment of your measuring device. Looking at the below example, we have an object that we're going to measure. Number 1 is we want to estimate the last value, 1 decimal place smaller than the value. This ruler, we're going to assume it's measuring in centimeters. It looks like this object is roughly here. That's our 41, that is 41 centimeters. Decimal, okay, that one looks like it's a 6. And if we zoom in even closer, you might not be able to do that with your page. You might notice that it is not exactly at the 0.6, but a little bit higher than that. But without the detailed gradients, increments, we don't know. But we can estimate that last digit. That digit we see there, it is 1 decimal smaller than the smallest increment. I'm going to estimate that is 41.62 centimeters. In this particular ruler, the smallest increment was in millimeters. So 1 decimal place smaller than that would be 1/10 of a millimeter, which is the 2 that we estimated together. Now, to write our uncertainty, we're going to write that as plus minus half of the smallest increment, which is half of a millimeter. That gives us 0.05 centimeters. That is an example with a stable reading. What about unstable readings, like your mass balances? Sometimes you get fluctuations, sometimes you get drafts in the room, so your readings might not be always stable. When you record your value, you want to wait until your instrument stabilizes. In this particular case, it looks like it's roughly 2.094, and we're going to assume this is measuring in grams. Let's think about a thought experiment. Let's say when you first put your mass on the balance, it read 2.093 grams, then it read 2.094 grams a second later. Then after another second, it read 2.097 grams, and then the last second it went back to 2.094 grams, and this is where it stabilized. When it stabilized, when it stabilizes, this is the value that you want to record on your data table. As for the error, when your reading fluctuates, note the range of its fluctuation. Then you write down your uncertainty as the difference between your stable value and the furthest fluctuated reading. In our case, this would be our largest fluctuating reading being the 2.097, not the 2.093. We take the largest fluctuating reading subtracted by our stable value, and this will give us our uncertainty, 0.003 grams, which you can write over here. So that is for unstable readings. Looking at the fluctuation, noting that error down. Anytime, now these are only examples that we've talked about right now. Of course, there's many examples of how to, in the lab, we cannot cover all of them. When you do perform a lab and you think that your uncertainty reading is not exactly how we've determined in this video, as long as you make a justification why you chose that uncertainty, you're doing good science. It's always, by a rule of thumb, it's usually better to overestimate your error than to underestimate your error. In our particular experiment, we did multiple trials. We did repeated experiments. That is a good way to help us decrease something called random error, which we'll talk about later. With more data, we will be calculating uncertainty differently. We take half of the range of our data. How that looks like is taking your largest value, subtracting your smallest value, and dividing that by all of that by 2. So look at your range, divide by 2. Because of the repeated experiments, you might want to get an average of your results, so that your final result, when you put your average and your uncertainty together, it looks like this. You got average, you plus minus your uncertainty. The way to write this properly follows another set of rules. There are 2 important rules for that. Your uncertainty must be rounded to one significant figure. 2, your average must be rounded up to the same place value as your uncertainty. We're going to look at the next example together, but I'm going to give you a chance to calculate the average of these 4 numbers by yourself. We can come back and compare our values, and we can move on to doing the uncertainty calculations together. Okay, this is a good time to pause your video, and we'll come back. Hopefully you have something like this, 9.38 seconds. Please do not round at this step, and also do not round after we calculated our uncertainty. Okay, so on our certainty, we need to take the largest value in our data set, which is our 9.550. We're going to subtract the smallest number in our data set, which is our 9.250. We're going to divide this whole thing by 2, which hopefully you should get something that looks like 0.15 seconds. This over here, don't forget, we do not want to round. No round. Okay, no rounding. When we have both of these values, our average and uncertainty, we are going to, first we're going to write this down together as a pair. We have 9.38 plus minus 0.15 seconds. The first thing we want to do is we want to round our uncertainty to one significant figure. Let's take that. Let's do that right now. We're going to round this guy. Using the 5, we're going to round the 1 up or down. In this case, it becomes 0.2 seconds. The next step is to take your average and round it to the same place value as your uncertainty. What that means is we want to make sure that this place value matches with the place value, the last place value of your average value. So here we look at our number and we look at, okay, we want our number to round to the 10th place, which is the 3. We're going to use the 8 and we're going to round this 3 up to 9.4. And this will be 9.4 plus minus 0.2 seconds. This is our final result. Below there's another example. I'm going to give you a chance to try this out yourself. We're going to come back. We're going to compare what we have. Here's a good time to pause. Alrighty, coming back together. So hopefully you have something that looks like this right now. The reason why I didn't complete this is because I want to walk us through the last step, which can look a little tricky over here. We want to round this guy, especially the uncertainty, to one significant figure. That means taking the 5 and rounding the 9 up. Now because 9 is going to round it up to the next place value, we here have 0, using different color pen, 0.1 second. And it's okay to round up to the next place value. Sometimes it happens. The another tricky thing is, now we have that, we want to also make sure we round our average this same place value, which means taking the 8 and rounding the 9 up. That's going to look a little troublesome because that rounds our number to 18. But we have to make sure that our place value in our average matches that with our uncertainty. And to do that, we add 0.0 so that the 0 matches that with the 1 in the 10th place in our answer. So here we have 18.0 plus minus 0.1 seconds. The reason why we do all this rounding is to do with how confident we are with our results. If you think about it, if we already 0.1 second uncertain about our measurement, does it make sense that we add, if we have 18.02756, all the trailing digits that follow? If we're already 0.1 seconds uncertain, it's really pointless to write all these trailing digits. If we're uncertain about that, we might as well do the rounding and leave our response the way it is. So conceptually, you can never be more precise than your uncertainty. That's the reason why we do this rounding. These will be some of the steps you will be taking when you're analyzing your data. Hopefully this video was helpful. Thank you for watching, and we'll tune in next time. Bye now.